Assalamu alaikum everyone. This is me Shuhaib and in this video I will show you how we can make a voltage regulator using a Zener diode. That means our today's topic is Zener diode as a voltage regulator. So first of all let's see what is a voltage regulator. A voltage regulator is an electronic component or circuit designed to maintain a constant output voltage regardless of variation in the input voltage or changes in the load connected to it. That means if you make a voltage regulator device, then you will make a device which will maintain the constant output voltage at its output side or at its output, whether you are changing the input voltage or you are changing the output resistance, the output voltage of the device will be always constant. Okay, so the output voltage actually on depends on the changing of the input voltage or in the changing of the load resistance. So you can say that in the other hand the device will act as a voltage supplier. Okay, so in this video you can also say that the Zener diode will work as a voltage source only. So if we move to the uh, video, if we move to the topic, then first of all we have to know that what is Zener diode. We have to know the Zener diode, right? A Zener diode is a normal diode, you know. What is a normal diode? No, the normal diode, in a normal diode, you know, if you make the forward connection or if you make the forward bias, then it will take 0.75 voltage first of all, and then it will let current flow through it without any barrier. That means it will become a short circuit after that. But if you make reverse bias condition, like if you change the polarity of the uh, biasing like this, make positive here and negative here, then it won't conduct any current through it. But if you keep increasing the voltage, the reverse voltage, then it will let current after a certain voltage, which is called avalanche voltage, right? But this mode of operation, or you know, this operation region is not good for this diode, because this voltage can hamper this diode and high current will flow, and this current also can damage this diode. So this is all about a simple diode. But when we go to the Zener diode, then we have to say that in a forward bias condition, Zener diode works completely as a normal diode. That means after a certain voltage, if we see this VI characteristics, then in a forward bias condition, after having a certain voltage like 0.7 voltage or something like that, 0.65, it will let the current flow through it without any barrier. That means it will work as a short circuit then. But when we make the reverse bias condition like this, it won't let the current flow at 0.75 or around this voltage. But if we keep increasing this voltage at a certain voltage, which is called Zener voltage, let's say Vz, then it will flow, it will let current flow through it. So you see in these VI characteristics, in a reverse bias condition, that means making positive here and negative here, we are increasing the voltage across this diode and it's not letting the current flow through it. But after reaching at a certain voltage, which we are calling Vz, it is working as a short circuit now, and it is letting a huge current flow through it. And another characteristic we can see from this VI characteristic graph, that is maintaining a constant output voltage, which is called Vz. We can vary a huge range of current across through this Zener diode. So we can see that after reaching a certain voltage, which we are calling Zener voltage, we can vary a huge amount of current through it, and using this characteristic of the Zener diode, we can make a constant output voltage device. That means we call voltage regulator. So let's say how can we use this characteristic of Zener diode to make a voltage regulator. Okay. So a voltage regulator circuit looks something like this one, and this is the Zener equivalent circuit. So if I say a little bit about this equivalent circuit, that we have to imagine a resistance of the Zener diode, which we are calling RZ, because the in the Zener diode a current will flow, which we are calling IZ, right? So with the variation, we are calling that the output voltage will be constant, which is Vz. But with the variation of the Iz, the Rz will have a voltage. So there will be a little variation in the output voltage. It won't be perfectly constant. So this what I wanted to say in this equivalent circuit. But if we move to the original circuit, that means the original voltage regulator circuit, we can have the supply voltage Vs, we have the current limiting resistance Rs, we have the Zener diode and Zener diode. Across the Zener diode, the voltage drop will be Vz, the Zener current Iz, the load resistance RL, and the current will flow through this load resistance will be VL, and this is the output voltage. And is on be the output voltage on be Vz all the time. So we can say Vz is equal to V out in all the cases. And in the circuit, Is is flowing. So we can say that Is is divided into two parts, which is Iz and In. So in this voltage regulator, we have two cases, right? First case, what? Vs will be constant, right? We won't change the input voltage, but we will change the output resistance, or we will change the load. So this is case 1. Output voltage will be constant, right? And another case is that we will vary the input voltage or the supply voltage, right? And we will keep the load resistance constant. And in this case also, output voltage will be constant, and for all the cases it will be Vz. So let's say the case 1 at the very first time. Okay, so if we move to the first case, we will make Vs constant, and we have to vary the VL or the load resistance. So moving to the first case, we have to understand the theory first of all, how these things actually works. Okay, so when this Vz is not in operation, then it will work as a short circuit. So I mean, sorry, open circuit. But as soon as it will be in operation region, and when it will operate, it will start maintaining the output voltage constant, which is called Vz. Okay, and we have this Zener diode. Okay, but with this we also have the current limitation of this. We can see the Iz is not only the Iz, we have the range of the Iz, that is Iz minimum to Iz maximum, right? Iz maximum. So what is Iz minimum and Iz maximum? Iz minimum is the current which will flow through this Zener diode when it will keep starting as a Zener. It will keep starting in working Zener region or in Zener mode. Okay, and if we keep increasing this current, it can take maximum current of Iz max, which will keep this Zener diode work in a safe region. Okay, so if you are Zener diode and you are yeah, you are giving whatever current you want, that means 100 ampere, 200 ampere. So it is not like that. It's not real. You can pass whatever current you want. You obviously have a current limit to make this Zener diode in a safe operation region, right? So we have Iz minimum and Iz maximum. Iz minimum is the minimum current to make these things operate in a Zener mode, and the maximum current you can pass through the diode is the Zener current maximum, which is called Iz maximum. So depending in this range of current, we have to make the range of the load resistance variation and the input voltage variation. So in this first case, we are working in maintaining the input voltage constant and varying the output resistance, right? So let me say you the theory is that we know in operation region when this circuit will operate as a voltage regulator, then the output voltage is constant. That means the circuit will something look like this one. Okay, the output voltage will constant, something like this one. And you know the is divided into two parts. That means the is will be is is equal to il plus iz. So if we vary the load, the IL will vary also, but the supply current IS won't vary because the supply voltage will see that the output voltage is constant. That means the no resistance is changing because the voltage is constant, output voltage. So it won't inject any current to the circuit. That means the IS is constant. So let's say if I'm making RL high, the IL will be lower, and where is the rest of the current will go because is constant. Then the rest of the current from the RIL in previous will move to the IZ, okay, in the Zener branch. So varying this output resistance will vary the IZ indirectly. Okay, this I wanted to say here. So let's say if I make RL at the lower, then IL will be at its higher position. So if IL is at its higher position, then IZ will be at its lower position also, because these two things will balance this IS, because IS is always constant. Okay. So in vice versa, if I am increasing the RL and making it its higher position, IL will be at its lower position, and if IL at its lower position, then IZ will be at its higher position. So indirectly we can see that when RL minimum, we have IL minimum, sorry, IZ minimum, and when we have RL maximum, we have IZ maximum. So we already know this variation, and from this variation or from this range we can get this load resistance range. So let's see how can we get that range now. First of all, I have to remove all of these things like this. And I know I am not doing these things in the smartest way, but let me do it, and let me take a little bit time. So now, if we take a KCL in this point, okay, let's say it's the point A, then we have to say IS is equal to IL plus IZ. Okay, if we take IZ in a side, then we have to write IS minus IL like this. And what is IS? IS is the current passing through RS resistance. And what is the voltage across the RS resistance? It is Vs here, Vz here. So the voltage across this resistance will be Vs minus Vz. And if we divide this resistance with this voltage, then we will have IS. Okay. So IS is equal to Vs minus Vi divided by Rs. And what is IL? IL simply the voltage across this load resistance divided by this resistance. So IL is equal to Vz. Sorry, here I have to say Vz. Vz divided by R. So we have to put these two values in these equations. If I put these two values in this equation, then I will have Iz is equal to Vs minus Vz divided by Rs minus Vz divided by RL. So In this equation we can see that we can make a relation between RL and IZ. Okay, so let's say this is the equation 1. So we have to get this RL value from this knowing range of IZ. So we have to put this RL as in a side. So if we say that then it will be RL is equal to Vs minus Vz divided by R minus Iz whole inverse multiplied with Vz. This is the equations. This is the equation that I wanted in case 2. So already I have said that when Iz will be minimum, RL will be minimum, and when Iz will be maximum, RL will be maximum, simply. So if we try to find out RL minimum, then I have to put Iz minimum, and theoretically we say Iz minimum is equal to 0. Okay, so RL minimum will be, if we put this Iz minimum, that means Iz is equal to 0, then we will have RL minimum is equal to Vs minus Vz divided by R whole inverse Vz. Okay, this is RL minimum equation. Okay, and if you try to find out RL maximum, then it is very much simple, which is RL max. We just have to draw the equation again. That's it. There is no any variation in this equation. Iz max whole inverse multiplied Vz. Okay, these are the two equations here, from which we can get the limitation of the load resistance or the load. Okay, so our first case is done. In first case we have seen that how we can make the output voltage constant, keeping the input voltage constant, varying the output resistance. Okay, so in our next case, what it will be? It will be the change in the supply voltage, maintaining the constant output voltage, and we will keep the output resistance constant. This is very much simple. Okay, it is quite similar to the previous one. So from the previous one we have written a equation which is Viz is equal to Vs minus Vz divided by Rs minus Vz divided by RL, right? So we have to vary this Vs, okay, from this, from the range of this Iz current. So we have to keep this Vs in a side, and let's make the rest of the equation. So Vs will be Iz plus Vz divided by RL. All the things will be multiplied with Rs plus Vz. So this is the relation between Iz and Vs in this equation, and let's say the equation is number 3. Okay, so it's simple. When Iz will be minimum, Vs will be minimum, right? So we just have to remove this Iz, or if you say we have to put Iz is equal to 0, because Iz minimum is 0, then we will have Vs minimum. So Vs minimum will be equal to what? Vz divided by RL multiplied with Rs plus Vz. Okay, so this is the equation to get the supply voltage minimum. And what is the supply voltage maximum will be? It is also simple, and who have understood all of the things can say it easily. which is Vs maximum will be when Iz maximum. So Vs maximum is Iz max plus rest of the things like plus Vz divided by RL Rs plus Vz. So we can also get the range of the supply voltage from these equations. Okay, so in this from this video, uh, at this moment we can have the range of the variation of the output load, which is we can say that RL minimum to RL maximum, and we have also found out that the supply voltage range, which is called Vs minimum to Vs maximum. So if you know the range of the supply voltage and also the range of the load variation, then you can make a safe operation of this voltage regulator. You know, you can properly make a voltage regulator, and also you will be able to know the safe operation of the voltage regulator device. So I think I could make you understand the voltage regulator circuit, and if you are helped from by me, then please like, comment, and do share, and obviously try to stay with me by liking my page. Okay, and so far I have to say bye to you. Stay with me, and we will see we will meet in the next video. Okay, bye.